let's take a quick example. Let's say find f prime of 2 where f of x is the reciprocal function 1 on x. All right. So if we were to use the definition of derivative at a point, right? So using the old way from, I guess, 3.1, you would have f prime of 2 would be equal to the limit as h approaches 0 of this function with 2 plus h plugged in, so 1 over 2 plus h, minus the original function with 2 plugged in, 1/2, over h. Okay, then we start to simplify. H approaches 0, and we'll get 2 over 2 plus h times 2 minus 2 plus h over 2 plus h times 2, giving them the same denominator, all over h. So we'll have 2 minus 2 minus h, so negative h in the numerator over, well, you'd combine these denominators, all right, they'd be the same. Right? You combine these, you have 2 plus h times 2 for this difference, and then this h will join that denominator, so you have something like this, right? H, and then times 2 plus h. Right? H's cancel, as we've seen many times before, and now we have the limit as h approaches 0 of negative 1 over 2 plus h. But then as h goes to 0 here, right, we'll have negative 1/4. And there's our limiting value for this derivative. So therefore, the slope of the function 1 on x at 2 specifically is negative 1/4. So now if I was asked again to find, I don't know, find f prime at 1, and by the way, find f prime at 3, and maybe, who knows how many times I do this, right? I need to find a bunch of different slopes for this curve at different locations. Well, this becomes really impractical, that I should have to use this limit definition over and over again with just a different value plugged in, right? I'd have 1 over 1 plus h and minus 1 over 1, and then perform this whole process, and then 1 over 3 plus h minus 1 over 3 for this one, and got to complete the whole process over and over again. Rather, what we can do instead is, could have done this a different way. We can first find, right? First find f prime of x in general. And again, what will that give me? That will give me the slope of the original curve anywhere I want. Then if I need to find it at 2, I'll plug in 2. If I need to find it at 1, I'll plug in 1. If I need to find it at 3, I'll plug in 3. Right? I'll have a single function, a derived function from the original, that I can then plug in any value I want and find the slope of the original function there without having to repeat this process over and over again. Right? That's the main practical advantage of having the derivative be a secondary function to the original, a derived function. And again, what is this derived function? It is the slope of the original for any x value. So now I'm going to go ahead and calculate the derivative of this particular function. Right? So f prime of x should be limit as h approaches 0 of 1 over not any particular value, just variable x plus h, minus 1 over, again, no particular value, just 1 over x for that original function, reciprocal function 1 on x. the algebra is very similar to what was done here when you had a particular value. It's not really that much different. The main difference is you only have to perform it one time, and you can use this rule, this new rule you're going to have, with many different values. So, repeating the same basic algebraic steps very quickly, I have 1 over, sorry, not 1 over, x over x over x plus h minus x plus h over the same denominator over h. Okay, let's have a little bit. And then combine the numerators together. X minus x is 0, so negative h is left again, just like before. This denominator stays the same, and the lower denominator scoots up to be with it. Right. H's will cancel. So we see we have negative 1, very similar algebraically to what we had before. Right? Just compare. Right? Negative 1, 2 plus h, negative 1, x plus h. The structure is basically the same. H is going towards 0, therefore we get negative 1 on x squared. All right. So now, whatever I want to find, if I want to find, in our example, it was f prime at 2, I can now just plug in the number 2 into this derivative function. So negative 1 on 2 squared is, of course, negative 1/4, which was the same thing we had before when we had the 2 plugged in for the variable throughout the entire problem. Right? But now this becomes much easier if I want to find, for whatever reason, the problem suggested such, f prime of 1. Well, what's that now? I don't have to repeat this whole process again. It's just negative 1 over 1 squared, which is, of course, negative 1. If I want f prime at 3, the answer is, of course, negative 1/9. You barely have to even look now. All right? So that is the main practical advantage of getting the derivative as a function, because then you can find the slope of the curve at any location by using that derivative function and not having to repeat the algebraic process for finding the derivative at a point for all of those locations.